Today, we're going to be talking about the contraction and relaxation of a muscle cell. When you go to lift up a glass of water or kick a soccer ball, have you ever thought about what is actually going on with the muscles within your body? The action that you performed, like kicking the soccer ball, is the stimulus or the thought that your brain sends to your neuron to tell your muscles to contract, which then causes an action potential. That action potential that came from you going to kick a soccer ball travels into the neuron to the axon terminal and hits the calcium channel, telling it to open up. This channel then opens out and allows the calcium that is on the outside to come into the cell or the neuron. This enters the neuron just like how people would go through a gate to get inside of a park. After the calcium comes into the neuron through the channel, it attaches to a vesicle inside the neuron that contains acetylcholine, or ACH. The positive charge of the calcium causes it to push the vesicle to the end of the neuron or the neuromuscular junction and therefore release the acetylcholine into the synaptic cleft, which is the space between the neuron and the muscle cell. Once the acetylcholine is in the synaptic cleft, where it is among many sodium ions, which are shown in purple, it attaches to the receptor glands or the yellow sticky notes on the muscle cell surface and signals for the receptors to open. After the receptors are open, numerous sodium ions flood into the muscle cell where potassium ions are already housed, which are shown in pink sticky notes. This sudden influx of positive sodium with positive potassium makes the cell more positive as a process called depolarization. If the cell is positive enough, it then sends another action potential or signal to the sarcolemma to continue in the contraction of the muscle. Once the signal is sent, it is unable to stop, which causes an all or nothing response. After the action potential is sent on the sarcolemma, the potassium items then want to leave the muscle cell because it is too positive and it's too crowded. Like if you're in a room and there's too many people, you want to leave. So because the Na ions are there, the potassium is going to leave through those receptor glands and end up in the synaptic cleft again. This process is called repolarization. And repolarization leaves the muscle cell, less positive than before. That action potential from earlier then travels in the sarcolemma down into the sarcoplasmic reticulum, which looks like an E and has those black calcium in it. Those black calcium then travel out of the sarcoplasmic reticulum because of the action potential and attaches to the actin. Once it attaches to the actin at its binding spot, it changes the shape and allows for the myosin heads to attach. Once the myosin heads attach, they move the actin to contract a sarcomere, which then contracts the entire muscle cell. After the myosin heads move the actin and contract the muscle, ATP has to come in and break off the myosin heads, or cut it off, so that it can chemically detach, because before myosin and actin were chemically detached. After it breaks off, it's ready to start a new contraction. This process is known as the sliding filament theory. After the repolarization and the sliding filament theory all cause the muscle to contract, the stimulus or the thought from the brain to the muscle cell stops. That then releases the acetylcholine esterase, which causes the enzyme to be active and helps to stop the action potential. That makes the gate shut and then stops the rush in and out of the potassium and sodium. This then allows the calcium to be reabsorbed by the sarcoplasmic reticulum as shown before, and the myosin heads to detach like we already talked about. Then it goes to the sodium potassium pump. This is a solute pumping method, which you have many in your body. It causes the sodium to leave the muscle cell and the potassium to leave the synaptic cleft to go back to the way that it was before. This happens by the first 3 Na entering the synaptic cleft, and then ATP coming in to open or shut the cleft and open the Na out into the cleft. Then, after the Na is in the cleft, the potassium from the cleft already goes into the pump, but does not require ATP, and only 2 potassium go in, and it does not require ATP for the potassium to then get shut into the pump and released into the muscle cell. And that is what happens when you go to kick that soccer ball.